Light is not...
That's fine, that's all. Okay, welcome back after lunch. I have a couple of announcements. One is that the network should now be working. The other one, which I'm very reluctant to do at the beginning of a session, in case you all dash out immediately to use it, is that for those who haven't yet found the terminal room, it's upstairs beside room E. So if you go from where we have lunch, basically straight towards the main road, and you'll find a door on your right with stairs, and it's up there, and there are lots of terminals just waiting to be used. So the next session is about attacks on the backbone and defenses for the backbone. We have certainly what looked to me very interesting talks. You're here to listen to them, not to me, so I will merely introduce Roger Spoor from SurfNet, who's been working on distributed intrusion detection systems.
Thank you. My name is Roger Spoor. I'm an account advisor at SurfNet, and I'm project leader of the SurfNet intrusion detection project. We started this project last year in August. We were hiring a few people, and well, they actually made the tools, and we have everything based on open source solutions. So even what we have made, everybody can download it and of course use it. First, we call it a distributed intrusion detection system, but some people call it a distributed honeypot solution. Actually, it is a distributed honeypot solution, only we have centralized the honeypot. So it's not really a distributed honeypot anymore. But that's making clear what it really is. We are putting sensors at customers, and we have a central detection system with a web interface. That's what it is in short. So we don't do anything with flow analysis. Last year when we started, we have made some goals, what we wanted to reach in the project. We wanted to understand what types of malicious traffic were at our customer local area networks. We were interested in the amount of traffic, in the spreading of worms within the local area network of our customers. The reason we were interested in this is that customers, they came to SurfNet, they asked to SurfNet, do we have a good security level? How do we do it in comparing to other customers? Do we have a safe network? And those questions were quite hard to answer. That's the reason we made these goals. For us, it was important to set up a scalable IDS solution, easy to manage, easy to maintain, of course. And we were interested in comparing the results between sensors. And as an ISP, it's quite important that you limit malicious traffic coming out of SurfNet. The second question is, why have we built something new? Because there were already honeypot solutions on sensors, but according to us, they were not maintenance-free enough. And we needed a solution that was easily scalable, easy to manage, so that it's easy to convince a customer that he should run a sensor in his own network. Third important thing is that we were interested in having no false positives in our detection system. Some traditional solutions didn't provide so we choose something new. Fourth point is SurfNet is a high-speed backbone. Every customer is connected at 1 gig or 10 gig. So this means that we thought, well, we were able to choose for a different approach, a different design in our IDS solution. And last point, we were interested in analyzing layer 2 traffic in the customer LANs. The general overview is like this. In the customer LAN, we place a sensor. The hardware is actually from our customer. The sensor will set up a VPN tunnel to our central server On the central server, we are running OpenVPN, that's handling the VPN connections, and we are running Nepenthes, that's in honeypot. In my next slides, I'll be more in detail about what we are actually doing on the sensor and the server. There's a second central server, that's our logging server with a web interface, and customers can log into the web interface. In more detail, what are we doing on the sensor? We have chosen to use Knoppix. Why have we chosen for Knoppix? Knoppix is able to boot from almost any hardware. SurfNet is not providing the hardware to run the sensor. What we do is we provide a USB stick, we send it to the customer, and he has to reboot a machine from this USB stick. The reason why we have chosen for USB booting is USB stick, we can remotely update all software on the sensor. That's very handy, so the customer doesn't need to maintain the sensor. And the second advantage of using USB is that customers are not able to use very old hardware, because only new machines can boot from USB stick. So in that way, we are sure that customers don't use an old 486 computer, for instance. What do you need to run a sensor? You need, for instance, a barebone. You can use a barebone. A barebone can boot from USB. We need one network interface. We use 2 times DHCP, or we use 2 times a static IP address of the customer LAN, because one IP address is needed when Knoppix boots, and the second IP address are we using on our server side. We actually get an IP address out of the customer LAN, and we are binding it to our central server. The third, what's needed is that our customers, they open a TCP port LF1194, because OpenVPN needs this port. And last thing that's needed is that we are using HTTPS for our sensor updates. Every sensor is checking every hour if there's a new version, and this procedure works via TCP port 4443. Not a standard port, but on the central server side, we run a honeypot. It's called Nepenthes. Nepenthes is a so-called low interaction honeypot, and it's capable of simulating all known exploits. In major, those are Microsoft-related exploits, but there are even some Linux exploits. And it's really simulating if it's exploitable. So an attacker, a worm, they think they can easily attack the sensor, the honeypot, and we are actually in control and logging everything in the database. Nepenthes is open source, is a very cool and very nice honeypot solution. On the central server, we also are getting the VPN connections from our sensors, and we are managing X509 certificates. We use X509 certificates to encrypt every tunnel, every sensor tunnel, and when a customer receives a USB stick, the first time it boots, it will receive its own unique X509 certificate, and it will be stored on a USB stick. So after the first boot, every USB stick has become unique. And we are connecting this certificate with the customer ID. Last thing we are using is source-based routing. And this is because there is an interaction between an attacker and Nepenthes. So there needs traffic goes back from Nepenthes to the attacker, and we have to route it in the right tunnel, OpenVPN tunnel. And we are only able to route it in the right tunnel if we are using source-based routing. The second server we are using is a logging server. We're running Postgres as a database. We have started with MySQL, but we had a few performance issues. So we have been migrating to Postgres. We run a web interface. Customers can log in. We can show statistics of sensors, groups of sensors. We can show them rankings of sensors, and customers can turn on logging via email. And I will give a live demonstration of this system. In more detail, how does it work? I send the USB stick to a customer. They put it on a machine, they boot, Knoppix is booting, OpenVPN will be starting. OpenVPN will connect to our honeypot and tunnel server. And this VPN, it's a layer 2 VPN. So our central server can put a DHCP request through the tunnel on the local area network of our customer. And it can bind the IP address of our customer on a virtual interface of our server. So our server is virtually put on the client LAN. So when an attacker attacks, he thinks he's attacking a machine on the client LAN, but actually he's attacking our server. Nepenthes is directly logging everything into the Postgres database. And then we can see the attack via web interface. Okay. Until now is how the current version of the IDS solution works. Now I'm going to tell you a few slides of our beta versions, because we are making improvements and additional features into the IDS solution. The first important feature to have is multiple VLAN support, multiple VLAN support. This is because a lot of universities, they have multiple VLANs, and they told me, well, Rogier, I want to run your sensor, but I don't want to buy 20 machines and 20 sensors, and so I need a machine that is capable of supporting multiple VLAN support, so that our sensor will be put on a truck, and that our customer can decide, okay, the sensor must be in 10 or 20 VLANs. And in our beta version, this already is working, and for every VLAN we are building a new OpenVPN tunnel to our central server. So in this way, customers are able to run a sensor in every VLAN they have. Next feature is multiple honeypot support. Because of our design that the honeypot is centrally, it's quite easily to add additional honeypots to the central server. On this slide, I'm showing how the current situation is like. We run Nepenthes on the OpenVPN machine. In our beta version, we have removed the honeypot from the tunnel server. Second thing we have done is we have introduced a private local area network on our central server side, and we have introduced a load balancing technique. Via this load balancing technique, normally the IP address we get from the customer LAN will be bind to the tunnel server. With this load balancing technique, we are able to reuse the IP address or to share the IP address not only on the OpenVPN tunnel server, but you can also use the IP address on Nepenthes or, for instance, Argos. Argos is another honeypot solution. Argos is capable of detecting zero-day attacks. Now that's a really nice feature. We're interested in adding this feature to our IDS solution, so now we are testing with Nepenthes and Argos in our IDS design. And if an attacker attacks now, we can choose on the tunnel server if the attack should be handled by Nepenthes or should be handled by Argos. Tomorrow, Herbert Bos will give a presentation in detail about how Argos is actually working. In future, because of the load balancing technique, we're able to add multiple honeypot machines on our central server side. The only important thing is that the honeypot we add to the central server, it must be capable of directly logging information into our Postgres database. And if it's capable, so we can easily add a new honeypot. Okay, now I'm giving a live demonstration. This is our interface, central interface on the web server. Now I'm logged in as an administrator, so I can see every sensor that's running or that's not running. Customers, of course, can only see their own sensor and statistics of their own sensors. In this overview, I can see the sensor number. I can see, normally I can see IP addresses of the sensors. Right now we have censored this information. And on the right side we can see if a sensor is green. Green means that's all right. Yellow means there is an update session or update is going wrong. And if the sensor is running red, then we are, well, now I'm only viewing the online sensors, but I can choose to view the offline sensors. There are a few sensors offline, and on the last fields I can see from which organization the sensor is. Via this web interface I can choose an action, I can reboot the sensor, I can turn SSH on or off, I can start or stop the sensor, so it's easily to control everything. Okay, now I'm going to show you something about the statistics, about the ranking of sensors. Over here, on top, we see that these are the statistics of this week, since Sunday. These are the statistics of all sensors. Of course, I can choose a particular sensor from a particular organization, for instance, but right now I'm showing the statistics of all sensors. We see what this week the top 5 of exploits is. So currently, this week, it's III's exploit is the number 1. But it changes because this is of this week. We are running this system since November last year. The statistics since November is definitely DCOM. DCOM is absolutely the number 1. In the system I can show a ranking of sensors. We can easily see which sensor is the number 1. Customers can see at what place they are in this entry. They can see if they are on the first place, the 10th place, but they can't see who is above or under them. As an administrator I can see everything. And we also make a top 5 of organizations, because organizations can run multiple sensors if they want. On the web interface, we made a search. Nice thing is we can search on a CIDR base, CIDR notation. And this feature was not able with MySQL. That's where we needed Postgres for. You can search on a source, this is the attacker source. You can also choose a certain attack. And with this page, this makes also clear what kind of simulations Nepenthes is actually doing. Those are all the simulations that Nepenthes does. And it works quite fast. We just are seeing all attacks from within a certain IP range. Most interesting page is this, I think. This is the log overview. First we see on top the possible malicious attacks. Possible actually means we don't know what kind of attack it was. It can be a port scan or something. So normally we say just ignore this. The second thing is malicious attack. And if we say malicious attack, it's for 100% sure it was a malicious attack. And then we can zoom in more. We can see what kind of malicious attack it has been, so what kind of exploit has actually been used. And customers can actually zoom in further. They can click on DCOM and see which attacker at which certain day and time, and we also are supporting passive fingerprinting. So we are capable of guessing what operating system the attacker is using. If an attacker did a malicious attack, normally the next stage is that it's offering binaries. It tries to compromise the machine. So this week there are 64 malware offered actions. We can zoom in, we see more details, and on the right side we can even see what kind of executable the attacker tried to put on the honeypot. And of course, Nepenthes is downloading all those malware. So this week we have captured these binaries. On the left side you see a unique hash value of the binary. On the right side you see what the virus scanners think about this binary. Now this list is not really impressive. If I go for all what we have captured since November, we see a more interesting list of all the different kind of malware binaries we have captured until now. This is really impressive. Lists. Okay. This is the log overview. Further, it's interesting to show you the check box. Via this box, we can show customers if their own IP range is within an attack. So some customers are not really interested in the attacks coming from outside. They just tell me, well, I'm only interested to know if a machine of myself is infected or is doing something harmful. And we put it in this, under this button. So customers over here can see, okay, right now, for this customer, 3 unique IP addresses have done an attack this week. And they did 13 malicious attacks on our sensor. Via this page, we are even able to show cross-domain attacks. So that an IP address of a certain customer is attacking a sensor somewhere else. We are not revealing the sensor IP, but we are showing to the customer, okay, your IP address did an attack somewhere else. We can make a few charts in our system. This is a chart about what kind of exploit occurred most often. That's definitely DCOM. In green, that's the DCOM exploit. We can make other charts. For instance, if I need to convince a customer that their sensor is seeing really a lot of attacks and there might be something strange in its local area network, I can show them this slide. We are able to show how many traffic is going through the OpenVPN tunnels. The top graph is about the aggregated traffic, and you see that we're only getting up to 50 kilobytes a second of bandwidth. So first we thought that we needed a lot of bandwidth with our system, but now we see we're running with 25 sensors. The bandwidth is low, the CPU isn't really being used. So the system is really performing very well. And the last thing I like to show you is the admin interface. And via this interface, customers or as an admin, we can enable email logging. Via this page, as a customer, I can choose this is my email address, and I want to show all attacks or just only the attacks coming from my own IP range? Okay. Are there any questions?
There's one down. Do you have a microphone down at the front, please? Thank you. I know hands always go up as far from the microphone as they can.
Thank you. In your opinion, what has been the main benefit for the users of your networks from this? The main benefit for the users?
You mean users in institutes or users in...
Users in general, I mean, has this network of this intrusion detection led to for instance, results like that you have been able to have less malicious traffic in your network, or heightened security, or the main benefit from the...
Oh, that's easily, I guess, because the customer, what the main of attacks, it's easily to show them that they are on the #1 list, that their sensor saw many attacks coming from their own IP ranges, and that's then easily to convince them that they should do something about their security policy. And there are customers that say, well, we don't actually know what's happening within our network, so now they are running our sensor, for instance, in their wireless network. Sometimes somebody comes in with a laptop with a worm on it, and now they are able to detect it more often.
Oh, there's one mic. Probably the last question, then we'll move on to the next talk. Just keep talking. It'll work. Yep. Nope. Maybe.
There we go. Okay, you mentioned using OpenVPN, and I saw a couple of things that caught my interest. I saw you were hitting port 1194 TCP.
Yeah.
Some particular reason for using TCP mode instead of UDP on OpenVPN? That's the first. Both questions have to do with OpenVPN. So.
I'm not sure why we chose it. It has something to do, I think, with the certificates we're using and encrypting tunnels with the X509 certificates.
Okay, and the second
and
question.
Keeping all traffic out of each other. That's not being bundled.
Okay, and then it may in fact be related to this. Then, have you run into any scalability problems with OpenVPN? Because in the normal operation of OpenVPN, you're spawning a process for each of your different VPN connections, and it's been my experience that OpenVPN rapidly runs into performance and scalability problems.
With 25 sensors online, there are absolutely no performance issues.
Oh, 20. Okay. 25 is insignificant.
But I assume 100 could be easily done. Easily.
The joint project used OpenVPN as a tunnel broker, and they even had to turn off encryption and a few other things just to scale to a couple hundred tunnels, just strictly because of the scalability problem there.
Okay. Well, the advantage we have is via our web server, we can push, or actually we set config files for every sensor on our web server, and sensors are getting the configuration. So if we have performance issues, then we are able to say to certain sensors, okay, from now on you should build a tunnel to another server. So I don't think we would experience any trouble in the future. At least I don't hope. Yeah.
Okay, thank you.
Thanks. Okay, thank you, Roger. The next speaker is... Sorry, yeah. The next speaker is... The next speaker wasn't going to use that microphone anyway. It's good. Do we have connectivity? It came out of there, so it should go back in. Talk to us. Let me guess, you can't see anything. Nope. Yes. Okay. Now you can see the presentation and we can see the presentation. The next speaker is Maurizio Aiello, who works for the National Research Council here in Italy and also lectures at the University of Genoa. Yes, he's getting it right. And he's going to talk about another approach, I guess, to understanding what's going on, this time by looking at existing logs and looking at not only the tool for analysing the logs, but also some work in progress to understand what's going on further from those logs, and in particular to look at worms.
Okay. So I will explain you the working of the software known as LMA, Log Mail Analyzer, which is a free software hosted at SourceForge. So the first question we ask is why should we look at analysis of log file? For example, the first answer could be to answer the user's request. It's normal that the user come to me and say, hey, I sent that email 2 days ago, but it never arrived. Why? Or for example, if you want to check the normal operation of your mail server. Or, as we will see in the next slides, as a help for performing worm detection. But do we really need a tool for making log mail analysis, or it is enough to directly look into the file? Well, a tool is useful because if we look directly into the log file, it is simple for us to perform some mistake. In fact, if you have a look to the postfix architecture, as you know, postfix is one of the most used mail server. We see a bunch of processes which cooperates among them, and each one logs directly into the log file. So, to retrieve the information we need, and only the information we need, it is a difficult task. But what information do we need about an email transaction? Well, mainly, I think that we need the timestamp, I mean when the email was sent, which was the client IP who sent the email, and the two fields, sender and recipient, mail from an RSPT to SMTP field, and the status. The status is that the mail is accepted or is rejected or is temporarily deferred. And we get all the needed information using the hash QID, which is in the log file. Here we have an example. Evidenced in purple is the hash QID, which is a unique hash, a string of a character, which is specific to a certain email transaction. And inside the log file, you can see that we have all the elements we need. Here we have the timestamp, the date and time. Here we have the client IP. Here we have the sender, the receiver, and finally we have the status. So LMA automates the job of reconstructing the email transaction by parsing all the lines and find each queue identifier and reconstruct the transaction, which could be a local-to-local transaction, a local-to-remote, and so on, according to the fact that the client IP is the mail server itself or not. This job is performed by the LMA module log translator, which, as we have said, parses the log file and as an output produces a plain text file where each line is a record with all the information we need. Of course, according to your network architecture, it is possible that you have to perform some customization. In the picture, you see my network architecture. We have a mail server. Well, this is a simplification. In reality, we have a 5-mail server. I have a mail server which before putting the mail in the destination recipient, bounces the email to an AV server, which is a server which performs content checking for virus detection, signature-based, and, for example, for anti-spam checking. After that, the mail is bounced back again to the mail server, and then it is put on the final recipient mailbox. So you understand that in this configuration, you don't want to monitor each mail that is sent or received. In the specific, you want to ignore completely the email which comes from the AV server. Therefore, we give the possibility of customizing LMA behavior. For example, by using whitelisting, as in this case, by using network selection, and as we see now, by choosing database format and server type. Once we have reconstruct each transaction, for data mining purposes, we need to store this data in a database. And for this purpose, we support two different options. We give the option of exporting and importing data in a transactional database, just like MySQL. And this has the great advantage that you can do very flexible query, and the engine power is very high, I mean, in terms of performance. But on the other side, of course, you need to have MySQL or other transactional database similar installed. And we thought it was good to let that LMA works as a standalone program without any need of other additional program on the server. So we had to build the database engine. Of course, the database engine, since it's custom, has not a big engine power, and flexibility of the query is reduced. We support only some raw query. The DB generator module is the module which accomplishes this task. The GenDB module built 5 tables. We use Berkeley DB libraries to help us in data storing, and as a consequence, we have a main table, which is the MailDB table, that has all the data we're interested in. And we have 4 helper tables, which are useful mainly in performing queries. This is the couple of keys and values for each database. The MailDB, as you can see, has one primary key, which is a simple progressive integer. And as the value, we have a string with the pipe-separated data we are interested into. I mean, timestamp, IP of the client, sender, recipient, and status. The 4 helper databases, instead, as key, have the value we are interested into querying, timestamp, IP address, and so on. And as value, we have the sequence of email number, which we will use as a primary key for the main database. An example could help us in explaining. Example, find all the emails sent from aiello@jcnr.it. You first search the string in the senderDB table. Since the senderDB table is an hash table, it is very simple to obtain the values. And we obtain the different values that are shown here, 27, 45, and so on. When we have all the different primary keys to search in the main database, we obtain all the data about each email. For example, the 27th record is this one shown in the slide. Of course, as I told you before, it is a very raw engine, very simple and raw engine. And so we allow to perform some simple query. For example, we can ask for all the email that were sent from a particular IP or from a particular sender, or whose time period was between a specified time interval. And with this simple program that is written in Perl for now, we should be okay with all the needs about system management and debugging. But what about security? Well, as you know, there is two different kinds of internet worms. Worms that I call direct, that uses directly buffer overflows or some other vulnerabilities to spread directly. And this, of course, you can use a packet filtering system to defend, or other similar systems. And there are some indirect worms that uses the SNTP engine, I mean the email, for propagating and spreading. For example, by attaching to some email, and then the email is forwarding to different users. So we think that since we have a tool for performing log file analysis, probably we could look for some worm activity in a network looking at the log file. In fact, we suppose that if a PC is infected by an indirect worm, probably we will have a lot of emails sent in a given short time period, for example. Or probably we could see that from the same IP, there are a lot of emails sent with different mail from field. Or, for example, we will observe some abnormal mail repudiation by internet server. I will explain better these three analyses in the next slides. And here we have a one-line shell code that was, in fact, the birth of the LMA software. With this line, you can parse an entire log file and find the top sender PC. Okay, so LMA was the starting point for another free project, which is called the Worm Poacher, whose aim is, of course, of studying the behavior of the email client with the purpose of detecting anomalies and take the appropriate countermeasures, if any. So the first analysis I want to tell you is about the number of emails sent. With Worm Poacher, we perform a calculation of all the email sent every 5 minutes, 1 hour, 4 hours, and so on. And this number is calculated, plotted, and analyzed. Here you see a plot of the mail activity of a mail server. On the x-axis, of course, we have the time. And on the y-axis, we have the number of emails sent. We distinguish immediately the 4 weeks in the months. And inside each week, we distinguish, of course, the 5 working days and the weekend. Inside each days, we distinguish clearly the working hour and the nights. Here we have the nights. And this could be a normal plot of normal activity. But for example, let's have a look to this plot. Probably this is not normal activity because we have the first 3 weeks in the month, which are similar among them. And the last week, on Wednesday and Thursday, we have some strange behavior because I see a lot of emails sent, and probably this could be an alarm for me. This is a sign that probably something wrong went in my network. But how can I perform this analysis? Well, as I did now, by visual inspection. But visual inspection is not a tool so useful. So it would be better to find a quantitative way, a quantitative measurement that is able to generate alarms to the system manager and administrator. Therefore, we tried to perform a baseline threshold analysis. I mean, we calculate the average email sent in a given period, and that's the mean. After that, we sum 3 standard deviation in the number of emails sent, and we consider this as our baseline. If at a certain time we have the number of emails sent which exceed this baseline, we are alerted. With the purpose of reducing false alarm, it is necessary to perform 2 additional tasks. The first one is that the average is calculated only during working period. With working period, I mean all the time interval in which the emails sent are above a certain threshold. Because if not, you understand that if I included the nights, of course, the average would be too low, and I would have a lot of false alarms. Another important task to perform is to correlate the different alarms coming from analysis in the 5 minutes period and in the 1 hour period. Because, for example, if a user of mine send an email to a huge mailing list, well, in that period, it is very simple that I have a baseline exceeding. But that's a false alarm, because that is legitimate email. So I have to correlate among different time periods, 5 minutes, 1 hour, 4 hours, and so on. Another interesting analysis that could be performed on Logmail could be the mail from analysis. If you own a PC, probably all the emails sent from your PC present a unique mail from address, which is your mail from address. Or probably you could have 2 or 3 mail from address, but not more. Here we have a picture about the behavior of a PC. On the x-axis we have the day, and on the y-axis we have the different email addresses used as mail from this PC. So you see that during this period of 3 days, there was a strange behavior, because from that PC, it looks like 80 different people used that PC. But it is difficult, because if that is not a shared PC or a PC that is used by students, it is not so possible. This method is a method used by some worm that try to increment their stealthiness. Because, as you know, the SMTP protocol is not an authenticated protocol, and therefore each one could set the mail from address as he wants. And the worm could do this, of course. And so this could be another aid for detecting worm. Another analysis we performed is the reject analysis. The first thing an indirect worm do when infect your PC is that it scans all the hard drive seeking for valid email addresses. It fetches the email addresses and it uses for sending itself to these addresses. But when it terminates this job, it could try some random addresses, just like jack at Microsoft.com, jack at novel.com, and so on, with the aim of incrementing the spreading infection. Of course, 90% of this email will be rejected by the internet server simply because the user is not existing. And so, even for the reject analysis, we perform a baseline calculation and threshold analysis with the purpose of generating alarms that could aid us in worm detection. So these are all the 6 different kind of analysis performed. on the number of emails sent, mail from addresses, and rejected mail. And we performed this analysis both on the global flow traffic. Global flow, I mean, I simply look at all the emails that are sent by users, or on a single IP basis. Single IP, I mean that I calculate baseline with these three analyses only relative to a single IP PC. And why do I perform this analysis? Because you could have some slow spreading worms that they spread, of course, they send them to other users, but slowly, with the purpose of being more stealthy. And if you have a large network, the traffic generated by this worm is low. And so your ratio signal-noise is very low. The only way to identify this worm is to perform an analysis based on a single IP. These are the results of 1 year activity during the year 2004. And in this column we have the data of the infection. Here we have the host, the infected host. And here we have the results using a global flow or single IP analysis. As you can see from this table, there isn't a unique way, a unique algorithm to identify all the different worms. But instead, we have to use all the 6 algorithm, all the 6 different analyses, cooperating among them with the aim of reducing false alarms and incrementing the probability of detecting worm. So, this is highly experimental. This is a decision support system which aids us to decide if a PC machine is infected by an indirect worm or not. We get all the alarms from the single analysis, and we multiply each alarm by a weight, and if the results exceed a certain threshold, we decide that that machine is wormed. So what could be future development of such a system? Well, we are at the beginning. For example, the first thing we should think to do is an automatic updating of the baseline, of all the baseline parameters. I say this because at the moment we only perform an offline analysis. Offline, I mean we take the history, we take all the log file and we analyze, and we found these different worms. But at the moment we are not able to perform online analysis. Another great improvement, we are already working on this and we are ready, is to implement the module SNTP sniffer. Because with the module SNTP sniffer, we could sniff the data directly on the wire, and therefore we can gain much more control over our data. Because, for example, in my network, I am the network manager, but I don't have the control of each mail server. With the sniffer, I can reconstruct the email transaction directly sniffing the data. I don't need to look at the log files which are owned by each single machine. Moreover, as you know, there are some worms that uses its own SNTP engine. And of course, as you imagine, I will never have the log files on the infected machine. And another good reason is that log file format is dependent on the mail server. Postfix has its own log file format, sendmail, another one, qmail, another one, and so on. If I directly sniff the data on the wire, it is more simple for me to reconstruct the whole transaction. And the last development we would like to implement is extension to ports different from 25. I mean extension to the methodology of baseline threshold analysis bound to an historical statistical data mining to other ports. Okay, that's all. Thank you.
Thank you very much. And the timing of your practice was spot on. Thank you. Any questions? No hands. I had one. Were you able to go to the source machines that you detected and find that there was a worm on there?
No, I wasn't able because since we performed an historical analysis, I found these results on July 2005, and the results were. But after having seen that there was a probable infection, I get a deeper look to the log file, and I've seen that it was clearly a worm. Because I know my users, and
They don't do that.
okay.
Okay. Thank you very much. This is a chair's dream. Everybody's talking exactly on time. Our final speaker in this session is Nico Fischbach, who works for Colt Telecom, where he is senior manager in charge of the European Network Security Engineering team. He's going to talk about the experiences of a major backbone provider in detecting and dealing with denial of service attacks. Your machine? Oh, okay.
Yeah, you know, anything fine.
Yeah. Whoops. This is a security session. We've screwed the connector.
Yeah,
in.
nobody's
There
going
we
to do that.
go. No. That's good. Helps the microphone.
And I turned my wireless off, so don't even try. Let's see if I'm going to switch it on.
Looks mildly promising.
Maybe not. Just okay. It starts to work.
Yep, there it is.
Oh, it's good. Good. Just a bit more time. Good. Thank you. Can you guys hear me? Yeah. Okay, that's all right. So yeah, I'm going to talk a little bit about what we see from a DDoS point of view in our backbone, being it from a kind of detection point of view, what's going on, you know, what you can do when you see it, how to respond, and one architecture we've been using to respond to these DDoS attacks, which is basically called network-based diversion. So first some statistics, and it's always funny to come up with statistics because everybody's network is quite different. So that's some data I took out of our DDoS detection system. In over 4 months last year, we saw 22,000 anomalies in the system. 5,000 plus are rated high. That basically means that those alarms make it to the security screen in the 24/7 NOC. All the other ones, medium and low, we just ignore. We just keep them for a couple of months for kind of statistics, or if you want to kind of do some forensics on some of the attacks. If you break down that number per day, it means basically that 40 security events show up on the security screen over the period of a day. And not take into account, you know, if it's a business day or just Saturday, Sunday. Some of them are duplicates of the same attack. The detection system isn't perfect, right? So some of the things maybe sees it 2 times. Sometimes with the host address, sometimes with the network prefix. So overall, you can say that we see 20 real attacks a day. That's kind of, you know, 1 every hour, which is already crazy to some extent. And in our view, a third of them, so let's say between 6 and 8, are actually affecting an end customer. All the rest, you know, it's just kind of some background noise, even for some of our customers. So far, so good. So just some stats. Last year in September, we got hit by a funny one, it was only like 200,000 packets a second, very distributed. So you see below the graph, you have all the things that scrambled out. Every single line is a different box where we saw network traffic being accounted for the attack. So you can see that I think we have like 60 peering boxes. I think every one of them saw part of the attack coming in, which is kind of crazy, because when you look at it, usually the attack traffic is always coming from one region. You know, it can be Europe, US, South America, Asia Pacific. But that one was just coming from everywhere, which is quite funny. We haven't seen many of those. And a couple of days before, and I don't have the graph anymore, we had 1 million packets a second. So it's maybe a figure that just I'm throwing out in the audience. You need to realize that some of the low-end routing devices you guys are using in your networks, they can handle 50,000 packets a second. So, you know, 1 million can still take down quite a number of the software-based platforms you guys are running in some of your backbones or part of your backbones. I'm not saying, you know, you can easily take down a GSR or some high-end Juniper, but, you know, depending on the engine card you have sitting in these boxes, like, if you guys have still some old T3 cards, you know, think Engine 0 DS3 cards, you know, they explode at 50,000 packets a second, and they affect the whole box. Another one, people are always saying, you know, oh, the largest attack I've seen, yeah, it's a couple of megs, we don't care, right? That one was nearly a year ago now, and it was already 3 gigs a second. So, and that one was hitting us pretty hard because it was coming from the US and Asia Pacific, and it nearly killed our US transit to some extent. We still had some free capacity, but it's kind of the largest one we have seen in the last 12 months, and it was just UDP fragments. Luckily enough, as you can see, it only took kind of a couple of minutes, so let's see, like 20 minutes to get it mitigated to a reasonable level, you know, going down from 3 gigs to less than 1 gig. So the customer impact overall wasn't that bad. So that was a funny one, right? So we have this DDoS mitigation platform we have in place. You know, we divert the traffic, we try to keep the customer up. And some of the attackers are quite clever. So they realized after 10 minutes, when you look at the blue and the orange lines, for example, that we are doing something about the attack, and the customer is still up. So you see that 10 minutes after, he comes back again, but from somewhere else. You know, that's the pink one you see on the right-hand side, you know, going down that way. So the guy found out that we are actually diverting the traffic. I think that one was only in the US. And he activated another botnet, and the traffic then was coming from somewhere in the UK. So, you know, kind of a clever guy and trying to play with us. It's fun sometimes when it's not Saturday at 4 in the morning. So, you guys would tell me, you know, why do you care, right? I mean, I'm not an NRAN, right? I'm a kind of commercial ISP and telco and so on. So, and you guys have these nice statistics about how much TCP sessions and whole large TCP sessions you guys can have over transatlantic links, and you have 10 gigs everywhere. And seriously, why the fuck would you care, right? Your core can probably carry more bandwidth than we can. And, well, you know, the attacks have changed. 1 year later, and those stats are coming from a study that Danny McPherson from Arbor did end of last year, beginning of the year. And we reviewed the stats together, and it was kind of funny because the largest DDoS attacks those guys reported, so it was like, I think, 65 or 70 different parties, universities, academics, hosters, service providers, tier 1, tier 2, and so on. And the largest in the statistics pack were 14 million and 22 million packets. So I don't know if you realize how much bandwidth, even with small packets, how much bandwidth you can fill. Not even talking about the routing and forwarding power and you need in hardware to be able to cope with it. So those two, we were quite surprised because those numbers look really, really high. So the two are big hosting companies, and they got really hit by such large attacks. And we got it confirmed because we spoke to one of their tier 1 providers, and he said he only saw 9 million packets out of those 14. And that hosting provider has like 4 or 5 different upstreams. So I think those figures are actually real. So, and I'm not even sure if a GSR or some Juniper can handle that many packets, but anyway. So it was actually affecting that customer seriously. The infrastructure provider, the tier 1 was providing the upstream, they were pretty okay. Didn't hit them because I think at least the tier 1 we spoke to, he was running a 10 gig core. And really some high-end no-tool boxes, so he could survive it. He could survive it, sorry. And in summary, most of the attacks those guys reported were in the 1 to 4 gig range. So that means that any larger tier 1 provider or large networks like GN can easily cope with most of the attacks. Unless you see some of the larger ones like 17 gig. I don't think any real provider can sustain 70 gigs more than a couple of minutes, because it's going to have collateral damage to some of the other systems. We've been quite lucky, and we've seen that in some of those reports. The bad guys are still using the same attacks we used to use when we were kids and fighting online. So the good old TCP SYN floods, ICMP floods, UDP floods, everybody has been talking about, those complexity type attacks where you actually try to find a weak point in a protocol stack or in a web application, this type of things. But you see such attacks, but it's maybe 1% or even less of all those attacks. All the ones we see, and you probably see in the graph, but that was probably a bit fast, were all the generic old school attacks that we use when I still used to go to university in engineering school. And the targets are still the same, they haven't moved really. So to some extent, I could say you're not affected. I mean, you're running a lot of IRC servers on your networks, usually for historical reasons. So those get hit pretty hard. But you shouldn't run adult or gambling or gaming sites. Some students probably do it at dorms or below their desk, whatever. But to put it into summary, what my view is that when somebody gets attacked, it's for a good reason. Maybe it's not a good reason for you, but for the guy attacking you, it's probably a good reason. And when you look at the stats for some of our customers, after a year or two, you just see the IP address in the reporting system, you know which customer it is. Because it's always the same top 10 or top 20 type of customers that you see being attacked, and always for the same reason. So we saw an attack, port 6667. And you talk to the customer, oh no, we're not running an IRC server. We are telling you you are running an IRC server. And maybe you don't know about it, but I can tell you somebody's got pretty mad after you. So you better look into it, and it's always, and then you have those stories, especially in the UK, with all the gambling sites that were blackmailed, the young kids saying, pay me 50 grand by next Saturday or your site is down. And they flew to them on Saturday and the site was down. And people start to react to it, and all the basic filtering mechanisms, I'm going to talk about it later on, you can use them to actually respond to the attacks and keep the customers live. And we haven't seen that many attacks really where they were using more sophisticated ways to bring the site down. The only thing you have to realize is that for most of the attacks, they got clever enough and realized that the basic trick most of the customers were using when being attacked is moving things using DNS, right? So pointing the web server to another IP address, or like Blue Security did, move it to typepad and 6 apart and take down 6 apart. So usually when you see some type of combined attacks, it's usually against the customer link or what's sitting behind the customer link and the customer's DNS servers to make it more difficult for the customer to actually move virtually his infrastructure to somewhere else or bring the attack somewhere else. But kind of that's really about it, and with those things you cover like 99% plus of those attacks. And if you want to shut down, that's not cool. Oh, back, sorry. The transit botnets. Most botnets are pretty small, so we have seen quite some cases. I think there's going to be a talk by Scott McIntyre on Thursday morning. He's got some figures that are damn impressive, believe me. Most of the botnets we have seen are more in the range of, a couple of hundreds to a couple of thousands. What Scott found with the TalkSpot form is in the millions. It's just crazy. I mean, we haven't seen such a bot network for quite some time. Luckily enough for us, most of the botnets still use IRC as their command and control channel. So if you can spot the IRC traffic and do some pattern matching or some behavior analysis on the IRC communication, you can actually spot the bots. There's going to be maybe something that Thorsten is going to cover tomorrow in his session based on the malware they found with Nepenthes. But you see that some of those guys actually moved away from IRC and tried to use web-based system to do the CNC, some form of peer-to-peer. We've seen one doing that a couple of weeks ago. They tried to obfuscate the things to make it more difficult to find out what's going on. One point that's pretty important and that you guys need to realize, and quite a number of people didn't get it for a long time, those guys have a clue and they are well organized. And sometimes those bad guys are much more organized than we are when it comes to doing things and how to react when something is going wrong and who's got the leader and who's got the follower and so on. So it's pretty funny. If somebody's after you for real, just don't ignore him and say, yeah, it's a script kiddie, I don't care. Maybe it's one, but if it's not a script kiddie, you better make sure you're well prepared to fight against. And the number of DDoS attacks on the internet is still really high, to say. But what's important to you? Everybody's been saying, you know, those guys, one day they're going to take down the internet. I don't think so. You know, the internet is their toy. You know, and what happens if you take away the toy from the kids? They start crying. So I don't think most of them to be stupid enough to actually shut down their own toy. And the other important point, and that's probably something Rob Thomas would have said in the morning in his presentation, you know, DDoS is only for fun, right? DDoS is here to piss off people. It doesn't bring any money. The people are using those bloody botnets to make money, you know? So DDoS, and it's just like, you know, you've been a bad guy, you know, I'm going to beat you up. But they would use all those botnets that they own for other purposes first. So DDoS is only kind of the top of the iceberg when it comes to the botnets nowadays. And the real things like, you know, credit card stuff and trying to break some things, or, you know, phishing and session hijacking and all these type of things when it comes to online banking. All these things, you know, are done with some form of botnets. And the main purpose of botnets nowadays is not just for DDoS anymore. When it comes to DDoS detection mitigation, we were looking, or we actually used some free open source GPL type applications, you know, CFLOD and this type of things back in the early days. And when you have a large network with lots of bandwidth, lots of network resources, you just realize that some of the free software that's being around, being it, you know, Flow tools or other ones, just don't scale anymore. And we had to move commercial for different reasons. So, you know, it's always an open debate. You know, do you want to run something open source, free, whatever, and put, you know, time and resources on it? Or do you want to invest some CapEx in a commercial solution and use that one to deal with the problem? And things have changed. I mean, when we picked the solution 4 years ago, I mean, that was the only commercial solution on the market. And there's a new free one, you know, by the guy from Switch, Peter Haag, NFDAMP and NFSM, which is kind of fantastic, and probably some of you guys are using it. And nowadays, I mean, I'm not sure if I would buy a commercial solution. I would probably get pushed to it because from an OPEX point of view, it doesn't really make sense. But just from the features side, I mean, it's pretty good. So you don't have to do commercial. The way we do it, we only get network data from the peering and transit edge of network. So all those network telemetry information or accounting information you get for every single flow that's crossing your backbone, we only get it from the peering and transit edge. We currently don't deal with anything coming from the access layer because our access layer is just too vast. We're covering like 60 cities in 13 or 14 countries nowadays. And we just have too many boxes, and it doesn't make, you know, commercially and from a licensing model sense to go for it. And we get every flow in 100. For the diversion stuff, I'm going to get back in more details afterwards. We use MPLS. Our backbone is MPLS enabled, so we can easily, you know, trigger things using BGP and create label switch paths in the network to carry traffic. We have put dedicated mitigation systems in the US because that's where we get most of our transit. We don't get any transit in Europe, so we only have transit in New York. So we need to actually protect our international link between London, Frankfurt, and New York. What's important too, I mean, doing DDoS detection and DDoS mitigation is one thing. But what you guys need to realize is to make sure that it needs to be part of a global security project. If you just do kind of net flow and some form of diversion, it's not going to help. So all the things we've been doing in the last couple of years proved to be quite helpful. So one thing that we have done, which is not directly related, is to hide the MPLS core. So if you're not sitting inside our core, you cannot talk to it. You know, we have a kind of a strong border towards the outside world, towards the internet. And you can talk to our customers, but you cannot talk to our core unless you're sitting in it. And that's one of the nice features of MPLS. You guys need to make sure you deploy correct policies of, you know, weighted random early discard. Make sure you don't have old engine cards. You know, engine is kind of a Cisco term for some of the line cards and engines. If you have old ones like think engine 0, engine 1, this type of things, if such a card is sitting on the attack path towards the customer, you can be pretty sure that if you get hit by more, let's say, than 100 or 200,000 packets a second, that box is just going to die because it's going to create a head-of-line queuing and this type of things, or head-of-line blocking, sorry. So even if you have like, I don't know, only 10 gig interfaces in that box and a bloody DS3 interface somewhere, and the attack traffic is going over the DS3 interface, while all the 10 gig ones will be, rate limited based on the DS3. So this is the type of things you need to keep in mind. I'm not a Juniper hardware guy, so maybe you have some type of limitations there too, or some of the other vendors. QoS. Do at least some basic QoS deployment to protect your routing protocols, the external ones, the internal ones, and your management traffic, so that if you get attacked, you still have a way to get to your boxes. Or if you don't do out of band, depending on the size of the network, I can understand that out of band isn't always the solution. The other thing that's pretty important, and there has been a clear trend in the last couple of months for people to move to it, is to do control plane policing. So, making sure that you protect the main CPU of your distributed hardware from basic attacks happening on the line cards. It's basically, rate limiting ICMP to the CPU, syslog messages. Talking about IPv6, IPv6 is always good fun because IPv6 is still done in software in most of the bigger platforms. So IPv4 is hardware is fast. Just send a couple of IPv6 packets and you slow down the box to like a snake. And same thing with IPv4 still. Some of the boxes, when you send let's say basic IPv4 headers, no problem, wire speed. Send IPv4 with some, options in the header, type of things, like boo, because everything gets pointed to the CPU. It's all done in software. So this type of things that you can resolve with control plane policing. And I would really recommend you guys to look into it. The other things we're doing is the different form of ACLs, access control list, kind of firewall, if you want, part of our network. You have basically three types of ACLs: transit, infrastructure, and receive. Let's take the last one first. Receive ACL is here to protect the box itself. So you're going to create one policy of ACL that is going to be pushed to all the interfaces, so that you can set up one policy for syslog, telnet, SSH access, SNMP, and so on. And you don't have to apply it interface by interface. You just apply it to all the interfaces in the box, which is pretty nice. Infrastructure ACLs, the ACLs, we use it in conjunction with the MPLS core hiding. Basically, that ACL says that any traffic from outside to the core is being dropped. And you also use that one to avoid spoofing into your core. The transit ACL is one that you shouldn't use. Let's go back. The transit ACL is one you shouldn't use unless something is really, really going wrong. A transit ACL is one that you would apply for traffic that's crossing the backbone going towards customers. And there, it's always funny when somebody puts a transit ACL on some of your core devices that says, oh, drop all traffic to port 80, and it's going to affect all your customers. So the only time you actually use transit ACLs, two times you use transit ACLs was SQL Slammer, because we really had to do something about it. It was killing all our backbones, being ours or other vendors, other ISPs. And the other one was the Cisco wedge bug, when you could just virtually fill up queues in all the CPEs. And when you have like 20,000 CPEs you need to upgrade, well, you need to come up with some form of mitigation. And then finally, make sure you have one TACAX box, one syslog box, or at least one place where you get all the identity management done and the syslog information being put together. And then you can do, like you did with the mail system, you use some scripts to actually analyze the logs and see what's going on. It's kind of easy to spot things in logs. Okay, the challenges we've been running into in trying to do that, trying to find all those bloody security features in all the hardware and software platforms we've been using. So you say, oh, control plane policing, let's do that. And you just take like 4 different series of hardware, 2 or 3 different versions of iOS, and you end up with a set of 12 different platforms that don't support the same things. And even the syntax is different, depending on the hardware or the software. So finding, a matrix where you can have a common baseline for all the features you need in the platform is kind of difficult. The other challenge we see coming up more and more is IP routing that's moving closer to the customer premises equipment. Today, most of the routing between customers actually happens at least in the access layer when customer I is talking to customer B. Well, today, you're moving that out to the DSLAMs or to the multi-service type platforms, Ethernet type services and GMPLS and so on. And those devices, they're coming from the layer 2 world. And those guys, security, they don't really care. The only security issue there is, can you flood my CAM table with too many MAC addresses or not? but they don't have the IP security background you will need to actually have some features on it. And when you turn them on, that they happen to be wire speed. One of them basically unicast RPF to make sure that customers cannot do IP spoofing. Well, quite a number of those vendors don't support it. So how do you do it? So you deal with it somewhere else, in your core, and it makes it very, very complex. Network counting can be an issue. In our case, we just do kind of peering edge and core. The access layer, we just have too many devices. I mean, it's not worth it. It's just too expensive. Luckily enough, we have only good customers, so they never send. They only get attacked, but they never attack anybody else. Cross fingers. So it's really. Let's put it that way. We've been quite lucky so far because I wouldn't get the budget to actually deploy network everywhere. The other thing is, everybody comes to talk to me and say, you're running a large network, you should do more about malware detection, botnet detection, and so on. And all those guys just didn't realize that you have to have a telco license to run a telco and an ISP. And that license means that you are not allowed to look into traffic unless you have to fix problems. And I'm not sure botnet is really a problem that is, legally applicable to the telco license. And we are in 13 or 14 countries nowadays, and even with the EU regulation trying to be kind of coming up with a common set of rules and laws for different countries, it's still not easy to just come up with solutions that would actually work and not break any of those laws or requirements. And the other thing we've been quite lucky so far is we didn't have to enforce our acceptable use policy that much. So the customers, actually, when you talk to them, they don't say, no, it wasn't me, and no, I don't have a problem, I'm not going to do something about it. And they usually listen, so we didn't have to run into the trouble of enforcing AUP or getting legal after the customers. But I know from my colleagues working at large ISPs that have a lot of end users, broadband, cable, DSL. For them, it's a nightmare. The only way to get something done by the customer is actually to enforce the AUP and cut them off. And I'm so happy to not be in that position because I would commit suicide. The other thing is customers. So when the customer knows that you do something about DDoS and that you can do something about DDoS, they expect the DDoS protection to be actually hacker protection. So we had customers calling us up like, oh, but you offer me DDoS protection and somebody broke into my website. And you've spent then the next 2 weeks with legal and the customer and whoever on the phone explaining them for the 20th time that DDoS protection and keeping the network up doesn't mean that you provide firewall IDS, IPS, security assessments, web application security, and whatever. So there have been some funny cases in the US where some ISPs got actually sued by some of their customers. And the other thing you're going to run into when you offer some form of DDoS protection or mitigation type thing is that the customer expects that solution to be perfect. So 100%, I'm sure I bought that from you, nobody can take me out. And those guys, as I said in the introduction, those guys are really clever. So they know how to go around some of those mitigation architectures you're going to come up with. And then the customer's going to get pissed off. Or, you have a large attack, and you usually say, you can filter between 90% and 98% of the attack. Well, when it's 1 gig, you still have quite, 20 meg hitting the customer. And if the customer's only a 10 meg link, what's the point? But he bought DDoS protection from you, so he expects you to filter 100% of the attack. So that one's really not easy, and it's more, so there's no technical solution to the problem. It's kind of, more making sure that the sales guy is not telling bullshit to your customer. The other thing that's coming up is the EU Data Retention Act, and some of the countries will have to keep data for quite some time. It's not really clear yet in most of the countries what kind of data you will have to keep, but there, it's expected that NetFlow will be the main kind of data source for the data you have to retain next to the HTTP dial-up and all these type of things. And the next challenge we run into is how to secure the VoIP core, but that's not the topic for today. Detection. How do we detect DDoS attacks? Well, the easy one is we just wait for the customer to call us. And that's probably the way you guys do it too. Once you get a complaint, you look into it. And, you have to, what some people still do is do hop by hop trace back in the core. And that's so old school, Unless you want to kind of, do job protection, that's not the way I would do it. Neither would I use just bandwidth graphs because it's becoming really difficult when you're running large networks, to see, what's 200 megs when you have 9 gig of traffic, it's such a small peak. It's not like before where you had like 10 meg and then a peak of 100 where you could see it. So it's easy to not see DDoS attacks in bandwidth graph when you're running large networks. So to me, NetFlow is kind of the only answer to that problem. And the architecture is pretty simple. I already explained it in the high level. So the blue boxes are actually peering and edge type devices, and you have them feed data into NetFlow collectors, commercial, open source, whatever you guys like. You then make sure it gets to a central place, and you're going to push those events into the NOC. And what you want to do, if you can, being it's time, money, resources, hardware, software, and all this type of things. Software is basically, does the access device you use to connect customers support NetFlow, and what kind of NetFlow, and what's the CPU impact if you turn it on? If you can do that, you can even, get the flows from the access layer. But I haven't seen that many ISPs that actually did that because it just doesn't scale, and the impact you have is way too large. Just to explain, I think somebody in the morning was talking about deep packet inspection. So what you guys can do to detect attacks and botnets and so on, and I don't want to go into the details because I know the NOAA guys are going to cover some of it tomorrow. Usually what you have, when you have malware, that's the yellow box you see on the host. The host is the blue one. It's going to set up an IRC communication. That's the red line with an IRC server. Usually it's a private, dedicated IRC server running on some compromised host. That's something that's not so easy to detect when you just do the sample NetFlow at the peering edge like we do. So there, what you want to do is doing some more DPI type thing on the access layer, where it's more easy to look into the traffic because it's less bandwidth. It's probably easier to put the boxes in. It's Ethernet because at the edge it doesn't mean it's going to be Ethernet. It's usually more kind of post type interfaces. Or 10 gig plus. Do you want to do TCP dump at 10 gig plus? I'm not really sure. So you can do DPI more in the access layer, close to the host, close to the attack source. The problem then is, if your access layer is large, so, we have like 60 cities. That means probably 600 or 700 boxes. I don't know how many switches we have. So even if you just want to have a span port on every switch, get it off to a DPI box, and then have the DPI box look into it. It means a lot of money, so I don't think, larger service provider, larger network operators can actually cope with it. And then again, if you have a network, a telco license, I'm not even sure it's legal to do it. And I haven't got our legal team to actually tell me, yes, you can do it, or no, you cannot do it. We're still trying to argue about the semantics. On the mitigation side, the most common one you still see is the BGP-based destination black hole. So someone is being attacked, what you do, you drop the traffic on your network edge to that IP address. Basically, it saves your backbone if you have a problem with it, but it just means the attack succeeded because the customer is offline, right? The complete system is offline. But I don't remember what the data was in Dennis' survey, but I think 80% plus of the providers or the respondents said, BGP-based black hole. ACLs, I hate ACLs because it's so unmaintainable and it's also, how to shoot yourself in the foot, right? And I'm really not a big fan of it, but I learned from quite some tier ones that they use it a lot, much more than anyone else. So we had a discussion how they do it, how they maintain it, how they make sure they don't screw it up and so on. And we found out that in their situation, the way their network is built, it makes sense, because the risk of doing something wrong is quite limited. And the place where they do it, they have the hardware and software capabilities to actually do it in a wide speed without any impact on the traffic. So ACL is something I think I need to reconsider myself. But, they're going to have a hard time trying to convince me. And then the last one, I'm not talking about the BGP-based source black hole because that one's useless if somebody spoofs, so easy to move around the IP space, is to divert the traffic to scrub it. And that's how we do it. So we have a regional deployment in place where we have some of the scrubber boxes connected via gig links to the core. And I have a graph, so you're going to see it on the next slide, and BGP sessions to all the edge devices. And at that point, you can already tell me, yeah, it's only a gig link. Yeah, that scrubber only has a gig link. So all those nice attacks, 70 gigs, how do you want to deal with it, right? Not even 10 gig interfaces. And the way we cope with that one is we have an IP anycast type deployment, so we can just add more boxes to protect. Still, it means we would have to have 17 boxes, which we don't have. So, but at least it makes it easier to scale up when you have a really large attack going on. The traffic diversion is using MPLS LSPs. So library switch pass, kind of a virtual pass in the network every time we need it. That one's figured by BGP. And the LSP is created between all the edge devices and the router sitting in front of the scrubber. And the way it works is that you have this LSP pass from the edge going to the box sitting next to the router. And the last box, the last router before the scrubber does what is called PHP, penultimate hopping. That means it just removes all the MPLS tags from the packet to make sure it just becomes an IP packet. But it does not perform a routing lookup. It just passes the traffic to the outbound interface, and that's really important. So that's the way it goes, right? So the box you see sitting at the bottom of the graph, just below the CCR, is a scrubber. And what happens is that one sets up a BGP session with all the boxes in blue. And that creates virtual label switch passes. I only put two on the picture, the two red ones. So all traffic coming from outside is actually diverted to that scrubber. Scrubber does the magic, tries to filter out some of the things. It can be any type of box. It can be a commercial solution, can be a basic, Linux, BSD-based firewall. It can be even, some type of commercial firewall, dedicated device. You can use different things. That box doesn't have to speak MPLS. You just want to make sure that you drop the traffic to it and get it inspected. And then once it's done, the traffic follows the green pass. And that one is not a virtual LSP because when you send the traffic back into the network, the traffic is following the normal routed pass. So you're not enforcing any diversion anymore. That's the way it's done to avoid any kind of routing loop in the network. The limitation for that solution is that you're only going to protect attacks coming from outside the network towards one of your customers. So if the customer you see on the right-hand side is a little green hard drive, if you want, if that one is launching an attack towards the internet, we can use that solution to actually divert the outbound traffic and look into it. It's really only dedicated to one-way traffic from the outside of the outside, that is the internet, into our network towards customer premises. Another approach that some people came up with to be able to deal with traffic flow in both directions is actually to set up VRFs. So virtual routing and forwarding instances on some routers on the path, so that they actually use VRFs to control traffic in and outbound. But for us, it was just too complex and not worth the effort. Last one, do you need a baseline? Well, if you have a baseline, it always makes it easier to understand what's going on and come up with the right filtering templates. So I would recommend, like everybody does when you do some statistics, come up with a baseline. It's always kind of useful. You need to make sure that you have enough capacity, because it's one thing to come up with regional cleaning sensors, but you also need the capacity to divert the traffic. So if you want to bring the traffic to some really hot spots, you need to make sure those hot spots are very well connected to your network core. You need to make sure that you don't have old engine cards when it's a Cisco device and no software-based platform on the path. If you have that, you're going to kill yourself. Shoot yourself in the foot, because you're going to create more trouble by diverting the traffic than just dropping it. Keep in mind that when you want to filter things, it's complex, right? It's like running a network IDS and just looking at 20,000 events a day. So make sure you have somebody that knows what he's doing when he's trying to fine-tune the things. It's easy to deal with most of the attacks. The only one that's really pissing a lot of people off, to put it that way, lately is all the DNS-based ones. Because DNS is on top of UDP, it's stateless to some extent. It's not easy to find out if it's a real DNS server behind, if it's a real request, if it's being a reflective attack. So DNS is really one of our headaches at the moment when there's such an attack going on. And the next one is going to be voice over IP traffic, because you have so many different voice over IP dialects when it comes to signaling. It's also some of the things that we're really breaking our heads on to make sure we can come up with some really good mitigation solutions. And finally, we've learned the hard way that customer reporting and the customer experience and what he is going to view about the attack is really important when you want to try to provide a service to him and he wants to know what's going on. So, just a mail saying, yeah, we're protecting you isn't enough. He wants to see, what you're dropping, how you're dropping it, and all this type of things. So, online real-time reporting is an issue, and most of the solutions, being it's the free ones and commercial ones, they're very limited when it comes to that. Done. Nobody's sleeping yet. That's good.
I don't think there was any danger of that, Nico. Apologies from the chair for that we've overrun a little bit, but I really didn't think you'd want me to try and stop that, even if I could have.
You would have lost.
I think I probably would have, yes. Any quick questions? I think you're around for the next few days, so I think feel free to grab Nico. Okay. Otherwise, I have been asked to remind you that there is an online feedback form which will allow you to influence how the conference programme is put together next year. Since I think I've volunteered to be on the programme committee again next year, I can personally say we'd look forward to receiving feedback to find out which topics you've enjoyed, which presenters you've appreciated. There are paper copies available, I think, at reception. But hey, we're network people, so let's use the online one and save anybody typing it back in again. And I believe there should now be coffee. So thank you very much, and thank you to Nico. Thanks. Gee, thanks.
Ero in montagna.
Sessions this afternoon. It is on wireless or wireless-related security. I'm glad to offer you 4 interesting presentations on wireless misuse, wireless security, also on configuring security policies, and finally on voice over IP security. Our first speaker is Pierre Ancel. Pierre Ancel. He worked as a researcher for INRIA and is now at France Telecom in the research and development department, and he's much concerned with wireless security, so we are curious what he wants to tell us. Hop, there you go. Which one was yours? Okay, so. Yeah, okay.
You hear me? Yeah. Okay. So I expected to have 30 minutes, but I only have 20 minutes, so I'm going to be probably a little bit fast. I'm going to talk about the issue of detecting misuses of wireless networks, and I'm replacing Laurent Duty from France Telecom. The agenda is the following. I'm going to talk about a few reminders on Wi-Fi technologies, but very fastly. An overview of possible attacks. We're going to talk about Wi-Fi corporate access architectures and different ways to deploy this kind of architectures. We're going to talk about open issues, and then the way we can develop and deploy a Wi-Fi intrusion detection technology. And then I will give, if I have enough time, feedbacks and recommendations on the way we can deploy this kind of architectures. The first standard of Wi-Fi suffered of critical security issues. So the security mechanisms were unable to satisfy authentication and data confidentiality and integrity. And the first standard suffered of conceptual weaknesses. The first one is that WEP, the crypto protocols WEP, is based on shared secrets, and it's a little bit difficult to manage in corporate environments. Today, a lot of publicly available tools allow to crack web keys and to inject traffic into wireless networks. So wireless technologies are critical from a security perspective because, and especially in corporate environments, any wireless deployment may have serious security impacts since you can't control the radio propagation, and the Wi-Fi access is anonymously reachable. So mastering Wi-Fi deployments in corporate environments is a very big challenge, and especially for corporate access and for Wi-Fi intrusion detection. So just a few words on the new standard that has been ratified in June 2004. We have new mechanisms for an increased security. It is based on 802.1x for authentication and for authentication. And we also have a flexible authentication framework based on EAP and the different EAP protocols, EAP, PAP, EAP TLS, and so on. And we have newly designed crypto protocols that replace WEP. The first one is TKIP, which is still based on RC4, but which patches the different flows of WEP. And the last one is CBC-MAC protocol, which is based on AES and is stronger than TKIP. And we have mechanisms for key derivation and distribution based on a forward handshake and group key handshake to derivate session keys. So I'm going to talk the different ways to deploy Wi-Fi access into a corporate network. The first solution is to deploy a Wi-Fi open mode. It means you're not going to secure the first access. It's like a hotspot. You are going to provide access to clients to the network, and then you use IPsec and layer 3 protection for confidentiality and authentication and so on. So here we don't use web because it's completely unuseful, and it does not improve the overall security level of the network. And also it's very difficult to manage. IPsec protocol is considered robust if we use an authentication system that is robust with certificates. And if we use also good crypto protocols like CCMP or TKIP. The second way to deploy a Wi-Fi architecture is WPA and WPA2. They are newly supported security mechanisms by the new standard, and they are largely supported since 2-3 years, but they are not easy to deploy. And we deployed them at France Telecom Research and Development Department since late 2003, and for WPA2 since late 2005. Okay, so I'm going to go faster on that. Some open issues. Protecting your infrastructure is a requirement, and for employees access and for visitor access. But you cannot solve every potential issue because some weak links subsist. The first one is on the client because, for example, Windows XP, when you connect to a Wi-Fi network, your preferred network, the network you are going to connect on goes into the preferred network list. And so, for example, here you connect it to Terrenagar 1, for example, and this network is going to go into the preferred network list of Windows XP. And then the auto-configuration mechanisms of Windows XP is going to try to find these Wi-Fi networks later. So, for example, in 1 week, if an attacker can create a fake access point and gain access to your computer by emulating an access point Terrenagar 1, for example. And in this case, the attacker will own the client, will own your computer, and try to get information from your computer, try to realize man-in-the-middle attacks, or try to go into open shares of your computer, or to realize exploits on your laptop. There is another issue on the client side, which is Wi-Fi Ethernet double attachment, since you can be connected to your corporate network and to have your Wi-Fi network switched on, and an attacker can gain access to your computer and can gain access to the network, the corporate network. There is another weak link, which is based on infrastructure, because you can come into your company and plug an access point, an open access point. And in this case, you are going to provide an anonymous layer 2 access to all corporate resources to everybody in the street, for example. So it depends on internal filtering policies, but usually you don't filter traffic from the plugs inside the network. You are going to filter traffic at edge with firewall or proxies. You may have security breaches with misconfigured access points, or everyone is potentially vulnerable because even though you don't have any Wi-Fi in your network, you can be vulnerable. It's like IPv6, like we said this morning. If you don't have IPv6 aware equipment, you may have problems. It's the same thing for Wi-Fi. Even though you don't have Wi-Fi deployed in your network, you can have problems. So the issue is how to detect and mitigate these security incidents. Wide supervision tools are helpless to detect specific Wi-Fi threats. For example, a fake access point which tries to own some employee laptops, a rogue access point interconnected with your wide networks. You can't also detect malicious activities like word driving or denial of service on radio side. So Wi-Fi intrusion detection is necessary. So if you listen to the radio, you will be able to know the clients and the access points that are speaking, between quotes, and you will be able to detect known attacks like MAC spoofing or word driving, traffic injection. So Wi-Fi intrusion detection goals are the following. First is to detect these equipments that can be a potential threat, to qualify them, to know if they are interconnected to the network or not, and to geolocalize illegitimate access points or sources in order to be able to switch them off or to unplug them of the network. So, Wi-Fi intrusion detection will automatically audit Wi-Fi access points in range thanks to deployed sensors. So it can replace periodic manual Wi-Fi audits, and it can allow the administrator to take proactive reaction when a critical security issue is detected. So the different kinds of countermeasures are the possibility to prevent clients from associating to a rogue access point or to a fake access point. So you are going to send, for example, the authentication or disassociation frame in order to prevent clients from associating to these access points. You also can. So it was on the Wi-Fi side, on the radio side. On the right side, you can also deactivate switch ports when you detect a rogue access point connected to a certain port of switch. But these kind of countermeasures need to be used carefully because it's not a good option to DOS, to realize a denial of service reaction on internal infrastructure or on neighbors, for example. So we designed a wireless IDS from scratch. It's based on a C language core detection engine, which is running on a WRT54G or GS, so it's a very light equipment. It is based on a flexible rule set thanks to a basic language of 60 signatures. We have inside this box an anomaly detection engine essentially for MAC spoofing detection. So this box sends alert in syslog to correlation equipment. And that realizes on-the-fly aggregation and correlation thanks to SEC, which is Simple Event Correlator. This is a tool that allows to correlate logs. We can also realize offline correlation to qualify access points to know if they are connected to the network or not. And for that, we use NetDisco, which is an equipment a tool that is going to discover in SNMP the network. And then we have an SQL storage and PHP presentation for administration. So here, this is the representation of the architecture. We have in red the wireless sensor that sends events with syslog to an aggregation and correlation equipment. This equipment is going to store alerts into an SQL database. And then we have another port. The administrator can console this information, these alerts on the front end that is going to query the database. So that's a different view of the same architecture, actually. So here I put some screenshots of the tool we designed. This is the panel that represents the different alerts, active alerts, the alerts in the last 10 minutes, and all the alerts in the table. So you have in APSYS the different security level and different classifications. So it allows an operator to know what happens on the Wi-Fi side. So here, this is a panel that is dedicated to access points. On the right, you have authorized access points. So it means they are access points that have been whitelisted because we know that they correspond to production access points into the network. So you have different information concerning these access points, like the SSID, the channel, the last time we have seen an event concerning this access point, and the number of sensors that have seen this access point active. So in the middle, you have a panel that corresponds to unknown access points. It means we don't know if they are interconnected to the network, to the corporate network, or if they are neighbors or hotspots. And on the left, you have rogue access points. It means they are access points that we have identified as belonging to the network because we discovered them onto the network. So you have different details on this panel. You have, for example, the IP address of the switch and the port number where we discovered this access point. So it allows us to switch off this port of the switch immediately, etc. So we also use geolocalization methods to localize access points or different equipments that are the source of attacks. So here, this is for a sensor, the curves that corresponds to. So in one curve is associated to a same range of power. And here, this model takes into account the propagation into walls, into buildings. So you can see, for example, that when we go across buildings, the power of the signal is decrease very fastly. So thanks to this model, we can correlate the information of the different sensors in order to try to localize the equipment that is the source of an attack. So for example, here you have 4 sensors in green that have identified an access point. And thanks to this model, we can localize this access point into this building where there is the red point. And you have other sensors in blue that didn't catch any signal from this access point. So if we can give feedbacks on this development of Wi-Fi intrusion detection tool, the first feedback is that the development of a robust wireless IDS is not a trivial thing because you need to handle a big amount of events. Building also an efficient front end for sysadmins is not very trivial. It's also very difficult to identify all interfering access points because sometimes we don't know if access points belong to neighbors or hotspots or are interconnected to the network. There is also a classic issue which is linked to false positive rate for IDS technologies, and this is very important to try to minimize this rate thanks to enhanced correlation. And we may have also performance issues due to the probes and the SQL tables. Is it okay for time? Okay. So I'm going to talk about the different requirements. So first, the overall requirements. It's very important to enforce a restrictive security policy, especially in risky environments. For example, in meeting rooms or labs, it's important to not to activate RJ45 plugs by default, and to activate port security and MAC filtering on switches. We need also to consider quarantine networks for guest access, different from the corporate network. It's also important to consider using IEEE 802.1x for your wide network in order to authenticate clients. And it could be good also to maintain a list of Wi-Fi equipments, of network cards and access points and configuration, but it's a bit huge to realize. You have also specific requirements for employee access. So it's important to use a robust authentication based on, for example, certificates. And we can use IKE with certificates for IPsec tunneling, or EAP-TLS for WPA or WPA2 smart cards. It's important also to use crypto protocols that are robust enough, like TripleDES AES for IPsec, or CCMP for WPA2. And you also need to take into account VLAN segmentation in order to make a differentiation between data frames and, for example, admin frames or authentication frames in the network. For client configuration, there are specific requirements. So first of all, if you don't need Wi-Fi access, it's very important to deactivate physically Wi-Fi and to remove mini PCI card. To use also a double attachment prevention system in order to deactivate, for example, the Wi-Fi network if you are connected to an RJ45 plug. And to clean also periodically WinExpress preferred network lists in order to avoid to be automatically connected to an attacker or to And it's important to use a well-configured firewall to enforce filtering, especially on Windows protocols. And for Wi-Fi intrusion detection system, they must be evaluated in terms of security because results are somewhat variable. And you may have also packet losses at the wireless sensors. And you can also tune your rule set for performance and effectiveness. But some attacks aimed at Wi-Fi intrusion detection systems tends to appear now, and we need to be careful about that. So we need to select solutions that have minimal impact on your architecture, have geolocalization capabilities, and use intrusion prevention techniques to use carefully. Okay. So to conclude, radio technologies have serious impact on security, and it's important not to consider them as negligible. And mastering wireless deployment is a global approach. You need to take into account 4 points. You need to deploy a restricted network security policy. You also need to harden the laptop configurations and to deploy a robust Wi-Fi employee access and a robust Wi-Fi intrusion detection system. That's all just some references about Karma and about an article that we did about design, implementation, and deployment of wireless IDS. That's all. So if you have questions.
Okay, thank you, Pierre. We have time for one short question. Can we have a mic for the...
Andrea Baldi, have you addressed in your IDS system the detection of ad hoc networks, which are basically equivalent of rogue access point, but on a client that you can turn on very easily?
Mm-hmm. Okay, actually we also handle ad hoc networks, but we did not focus for this proof of concept on this aspect, on ad hoc networks. But it's also possible to do that.
Okay, we have to hurry on, and I would like to switch to the next presentation, which is only partly related to wireless networks. It's related to homogeneous configurations, simple configurations of networks. It's by Florian Pester, who works at the Regional Computer Center of the University of Erlangen. He recently, or not long ago, achieved his diploma or master's degree on the work on security, and he's now working as a network researcher in the computer center.
Okay.
Yes, you like.
to switch it on.
Good afternoon, ladies and gentlemen. My name is Florian Prester, and I come from the IT Center of the University of Erlangen-Nuremberg. And I want to talk to you about security within networks and with ease and one command philosophy. First, I want to give you a short overview what I'm going to talk about. I want to give you a short introduction, where I come from and why I look on security within networks. Then I want to give you the little steps what I mastered to do to achieve security within the network with ease and one command philosophy. There we start with filter list validation and filter list creation and go on to filter list management and exchange. And last but not least, I want to show you two scenarios where this can be used and how this can be used. On this slide you see our part of our network. We are a universal network with a distributed campus on 3 cities, Erlangen, Nuremberg and Fürth and some other parts. And we have many routers within, and we are layer 3 networking. And within this network, normally security is not easy to achieve because you don't know where someone is and what happened. So there are some questions we have to answer. First, if a security incident occurs, is what system is affected. This normally I can look up, or I get a report or someone is calling and telling me that a system is under attack. Then what service is under attack on the system? Then there comes the major question, what can I do to ease the situation? Normally within networks, I can block traffic from one host, or I can deny access to a specific service on borders between local area networks, between campuses, between cities, between the networks. But I need to know where. Even if I got an IP address, normally I don't know what is the next router or the next firewall where I can block this host or this bad guy with this IP address. And last but not least, I don't know, sometimes I don't know how can I block this IP address, because I have different systems of filtering systems. I have different architectures. Maybe the guy who is normally in charge for the filtering systems is on vacation or he is sick. Then what can I do if I'm not familiar with this system? Therefore, the approach I developed is taking away the where from the administrators, as well as it's taking away the how. So the administrator or the administrator in place just needs to know what system or what service and what can I do. So he needs to make the decision, I need to block this host or I need to deny this service. Within networks, security mostly depends on traffic filtering network traffic. And this is normally done with some kind of filtering system like checkpoint firewalls or Cisco firewalls or Juniper firewalls, and there's a Nortel outside, Nortel firewalls or some open systems. But all of them are in common that a normal filtering system is only as good as the filter lists, and the filter lists depend on the filter rules inside the filter list. Unfortunately, the filter lists are not very handy for the administrators. They all look very much the same, and there's an example from the Cisco system, extended access lists. The administrators like to overlook some details. So we see here 5 filter rules, and normally we have 50 to 100, 200 or even more filter lists. And if I misconfigure one single rule, I can ruin the whole filtering system, because mostly those filter systems are going from the top and running so-called first match paradigm, where the first matching rule is taking action on the network traffic. So to understand those filter rules, we have to analyze the filter rules inside the filter list. The first thing is I decided to analyze this filter list offline. I will not go on the filtering system and decide, okay, I try to block some system, or maybe let's see if I can block the system now. So, because I need to have a surrounding where I know what I got and where I need to go next. To analyze filter lists, I have to do two issues. First, I have to analyze it syntactically, where I can find the typo errors, can identify invalid options, wrong syntaxes, which may appear if I'm used to another system normally. And all those can be done by developing a parser, which is parsing the filter lists and knows the grammar of a filtering system. And then it tells me I have swapped to letters, or this option is not available for this specific systems. But there are also another kind of error class. It's the semantical errors. What is a semantical error? For me, a semantical error is an error which hinders a filter list to do what it's supposed to do. So I need to know what is a filter list supposed to do. And it's very important to understand I do not want to know what a filter list is supposed to do in generally. But I want to know if the configuration of a filter list, as I see it now, is semantically correct. So if it's consistent, or if single rules within the rule set are hindering each other. If one in front is shadowing some successors of it. So, for example, we have a little filter list here where we permit the access to a specific host using secure shell, and then we deny the traffic for the rest of the subnet. Now, if you switch, if you flip the first two lines, and we deny first the access to the subnet, and then we want to allow the access to a specific host using secure shell, it will never work, because looking at Cisco access lists, there is a first match paradigm where the first matching rule is taken action. These kind of errors I need to be able to detect, and it shows me that this can't be what I wanted to do. But it only shows me that it can't be what it wanted, but because maybe I wanted it. But it's very important to detect this kind of errors. There are also some advanced inconsistencies in filter list analyzing. When you're looking at a firewall, and we have on the one side we have the bad internet, on the other side we have some subnet we want to protect, there are so-called unrelated rules. Unrelated rules are rules which match traffic that never can show up on this filter list or in this firewall. For example, I have the statement I want to protect a network with the network address 121.131.23.0. So we have class C network, and we want to protect this network, whatever the syntax might be. But if I switch a single number to the network 121.113, which can happen if I'm in a hurry, or if I'm under pressure, or if I just didn't pay enough attention, then the firewall will do so, but then the traffic will never show up. And then it depends on the firewall if the network is safe behind the firewall. But it is important that the administrator thinks he added the rule, because he actually added it, but he added a different rule set. Also, so-called forgotten rules. Looking at the router, for example, and looking at stateless filtering systems, we have to look on a connection with two directions. We have one to the target and one direction back to the source of a communication. And therefore we have two filter rules. One allowing or denying a filter connection, and one allowing or denying the way back to the source. And if I forget one of those to filter rules, then there can't be any connection between the two hosts. Or, in the other side, if I want to prevent a connection to be established, it can be established. Those inconsistencies can be detected if I use the information which is already there. If I use the information around the firewall, if I use the information which is provided by the network. And detecting errors is one thing, but then I have already done the mistakes, and the better thing is to avoid mistakes. Therefore, I thought about it, but if I can detect filter lists, errors in filter lists, maybe I can create filter lists as well. And on the creating filter lists, there is one way to go is using a macro mechanism. I think a macro mechanism where we use an easy syntax, little information to remember about the networks, and system independence. So I use a language which is not relying on the system. Then I have an easy-to-use mechanism which produces less errors, because I can't deny that no error will happen at all. But I will have more security. Now, what is this macro mechanism? The macro mechanism is suitable for filter rules which it's suitable for any filter rules, but it's used in places where I have the same situations in different networks. So I use the same filter rules with different informations. And also, if I use the macro mechanism with describing words, I have a much more describing filter list instead of complicated filter rules. And everybody, if someone sees a filter list containing some words like anti-spoof or DHCP or block service something or block host something or NMS, then people related to networks know there might be a network management system, there is an anti-spoofing mechanism, and depending on the arguments, I know maybe there is a server behind the service, or I have clients for the service. And here I show you an example how this might work. We have a two-level abstraction. We have on the one side, we have a so-called meta filter list, where we add the macro words, the keywords for a macro mechanism, and, for example, some filter rules. Of course, then I'm not system independent, but I could avoid adding filter rules in the meta file list, but I didn't want to. I wanted to keep it this way. So when we have the meta filter lists and we expand the macro mechanism, then we have on the right side the valid filter list with the expanded macros. And looking on the left side, we have the macro block host with an argument as an IP address. So everybody knows when someone sees this keyword block host and afterwards an IP address, normally you think, okay, this IP address might be blocked. It's what the keyword says. So on the right side, we have the rule deny IP host the IP address and then to where. Or on the other side, we have deny IP from anywhere to this host. But important is we have the macro block host. Here. We have the macro block host, which gets expanded to this rule, and the information handed over is inserted here. So I can block any host if I know the network, and let the filter list be expanded. Or I have the macro block anti-spoof, where no argument is given at all, and on the right side I have two rules which use some depending information, depending on the local network where this rule is inserted to. This information is leading to the extended macro mechanism. When I have information around the firewall, then I can use this information to customize the rule sets from the macro mechanism, depending on the on the kind of network which I want to protect or which I want to control. And one important thing is for this filter list is to control the order of the rule sets. I want, if I have the first match paradigm, I need to know if the blocking filter rule is really inserted before any allowing statement where the filter rules or the filter where the traffic for this host might go through the network or through the firewall. This I need to do. On the other side, I have different information about the lanes or if it's a backbone, and then I need to customize the filter list as well. But very important is to keep the administrator in charge, so the administrator can disable all this nice automations with only very short time of action. Combining this, we can almost do kind of a filter list management because we can validate and we can create filter lists. Then we have the information about network topology around in our network, and we need some kind of versions management so we can follow the history of the filter list and who changed something in the filter list. And one very important thing is to exchange the filter list on the filtering system. I'm offline somewhere in the network and I'm editing my filter list, and then I need to get them onto the filtering system. There I need to have the distinction between the installation process and the activation process. So I need to install the filter list on the filtering system and get feedback if the filter list is syntactically correct because I checked it offline before. And after that, I need to activate the filter list, and if the filter list gets activated, I need to be sure that the filter list is activated in the place where I wanted it to be. This implies that I can compare filter lists. I need to compare the installed filter list with the filter list on the offline system, on the central management system. Now I want to show you two scenarios where this can be very helpful. The first is blocking a specific host somewhere in the network. I have a malicious system detected somewhere in the network. Someone told me this IP address needs to be blocked. And first, I need to find the system which is filtering this local area network, which is this one here. And then I need to edit the filter rule sets for this system on the firewall management system, which is the green ring here. Then I need to create the filter rules using this macro mechanisms. And if I use the block host macro, I only need to add the block host macro with this depending IP address on it into the filter list, into the meta filter list. I need to create the filter list and validate the filter list so I can be sure no mistakes happened. And then I need to update the filter rules on the filtering system on this next hop router of the system. And then the malicious system is blocked, and the only thing I needed was the IP address of the malicious system. And the network is safe again. The second scenario is, looking back, we had a Sasa worm, which spread around the networks, and I needed to close down a specific port on all local area networks throughout the network. So I have a malicious service, and I detect which routers or which firewalls are affected by the service, and I edit all the filter rules which I wanted. I create the filter rules again with the macro mechanism. I validate the filter rules if no one else added some filter rules which might be hindering now, and then I update the filter rules on all the systems at the same time, and all services are blocked on all firewalls. On every firewall, the system is blocked, and therefore this system, the network, is safe again. Now, why it's easy in one command? Because the administrator controls the whole process. There are single steps: the validation, the creation, the updating of filter lists, the controlling of filter, which the administrator can combine individually. We have one command. If I combine all these single steps to one command, I can, for example, the block host we established in our network by the block host command, and now everybody within our network stuff can block on any system a specific IP address. And the administrator stays in charge all the time. So this is all, there's no action taking place which the administrator can't deny. As a conclusion, I want to say that we can detect syntactical and semantical errors offline. We do not rely on any system which improves the security. It's an easy management of filter lists because I can use a surrounding where I'm used to. I can react very quickly on malicious systems or services. If time is fleeting or I have pressure or my boss is in my neck, I do not have to think about what the filter rules might look like. I can have, if I have the right macro defined, I need only 2 words, and the filter rules are inserted and deployed. I can easily control the filtering system, the installed filter list on the filtering systems because I compare filter rules. And last but not least, this whole system is prototype active and reliably running on our campus and is written in Perl. Thank you for your attention. And do you have one question?
Thank you, Florian, for addressing these very practical issues. We have time for 1 or 2 questions.
Yes.
Can we have a mic here?
Okay. I suggest, no, I guess that you have a micro that is vendor specific. Is that right?
Did I have what?
The macros that have
macros?
used so far are vendor specific. How do you generate the access list right now? You have a configuration file and some macros that take the configuration file and produce a vendor specific access list. Is that right?
Yes.
Do you have any plans to have, let's say, a more open tool that you can have some configuration at the beginning, saying that this equipment is this vendor, so you use these macros and it generates the access list, and if you change the configuration at the beginning, it's another vendor's.
Yes, this is where I want to go next, and where I'm working on and looking forward to meet some people who have experience with it. And I want to go there that I am vendor independent and can generate filter lists for any filter system. But this is kind of a handwork doing, I think so. So this might take some time to solve all the vendors. But until now we do only the Cisco access list because the most rudimental filtering system with the less the comfort at all. So we stick with the access lists.
Is there another question? Well then, I would like to pose one. I mean, you were addressing the issue that configuring filtering coherently in a network is a semantical issue, and you're using a macro substitution mechanism, which is a syntactical mechanism. Are you thinking of redoing this by, in a framework that is carries more semantic, has more way to individually control what you're doing?
There's the difference. The macro mechanism is very, very easy, but it gives the administrator a lot of comfort to not think about syntax in that point. You think about the syntax once and then you reuse it. It's just a reducement of the complexity of the filter list. But the semantical issue is by analyzing the filter lists. I want to detect errors within filter lists which are syntactically correct. There's semantical until now. But you're right, that's again the next step where I want to go to do kind of a framework where I can put the semantical also in the creation of the filter lists.
Okay, then let's thank the speaker again and move to the next presentation by Josh Howlett. Josh comes from the University of Bristol and is a networking expert there, being concerned mainly with security and authentication in mobile environments, and he has been borrowed out, as far as I understand, to Janet to implement the wireless security in the Janet roaming system. And you will speak about this, aren't you?
Yep, I hope so.
Oops, but this is not your presentation.
I'm the awkward person.
Full screen, here we go.
Okay, thank you very much. Hello everyone, my name is Josh Howlett. I'm the Janet Roaming Service Technical Support. I'm at the University of Bristol, but I spend most of my time working with UKERNA. How are we doing for time? Are we still 20 minutes? Yeah, okay. Just a few objectives today for my talk. First, I wanted to promote the Janet Roaming Service and EduRoam in general. There is another sort of parallel session that's concentrating on EduRoam, so I'm not going to talk about too much. But the Janet Roaming Service is basically the UK's instance of EduRoam. We just give it a different name. The most important thing I want to stress today is to provide an understanding of the issues that are exposed in wireless roaming. This is so not just wireless technologies as such, but all the new security issues that come out when you enter a roaming environment, where users are going between different administrative domains. Some quite surprising things happen, and that's mainly what I'm going to concentrate on. With these issues, we had to solve them when we were designing the JRS, and I'll be talking through how we did that and how these issues fed into the design of the JRS, and I'll be explaining that. And then finally at the end, I'll discuss some new technologies, many stuff that's undergoing standardization at the moment, that's intended to improve security for wireless roaming or just roaming in general. I should stress that, before I go on to this slide, although again this session is about wireless, a lot of what I'm going to say is also applicable to wired networks as well. In the terminal room here has RJ45 ports as well as the wireless network. So roaming isn't just about wireless, it's also about other kind of access media as well. It's just that wireless is obviously the most popular. This is the EduRoam map. Everyone here has probably sat in the presentation already and seen this one. The green depicts those countries whose NRENs are participating in the EduRoam Federation. And you can, in principle, if you come from an EduRoam enabled site, connect to another EduRoam enabled site in that country. Just very briefly about UKERNA, they manage Janet, which is the UK's academic network. I was flicking through their website just the other day recently, and something struck me. It's just this section here, which is the concept of community underpins everything UKERNA does, and that UKERNA offers many feedback mechanisms. And this is part of their mission statement, which these things are often full of complete rubbish. But UKERNA really do talk to the community. And one of the ways in which they do this is through something called the UKERNA Wireless Access Group. UKERNA set this up in 2003 in response to interest from the UK academic community in wireless networking. What should we do with it? Where is it going? Is it useful technology? This is something that we were brought together to look at. And one of the things that quickly became apparent was that people wanted the ability to be able to go to another institution and connect to the network and get network access. It's a very useful tool for all sorts of environments, and just looking at the people here in this room with all your laptops open, it's something that people really, really like. We had a few sort of general requirements. It had to be secure. It had to be easy to use. And the most important, in a way, is that the organisation from where the users are coming from, the home organisation, has to be responsible for supporting the user and for the account management.
So the idea is to alleviate all of the problems that you typically have with visitor access, which is visitor accounts and disseminating the credentials to visitors when they come on site. The idea is that a visitor should be able to go to another site and use his credentials from his home organisation to authenticate against the network and get network access. So security aims. Authentication. Authentication is just saying, who are you? And being able to say with a good level of reliability, but we know who this person is and where they're from, and we can go and beat them up if they do something wrong. The second thing that people are interested in is enforcing acceptable use. So you may be able to do web access or IMAP access, but we're not very interested in letting you do SMTP, because you might go and spam some people, and then our institution gets added to the blacklists, and we can no longer send mail, and all of this sort of thing. So enforcing acceptable use on visitors is very important. Accountability is also incredibly important, and obviously relies on authentication. Accountability means that we have to be able to prove and demonstrate to someone that they have done something wrong, and then you can beat them up. And finally, this is sort of an axiom of security in general, really, which is the principle of minimal privilege, which is where you should never tell any party anything that they don't need to know, unless they really, really, really need to know. And this is an important principle in the EduRoam, Janet Roaming Service context, because there are a large number of people involved in going, or people or network devices, or all sorts of things. There's a lot of infrastructure that's required to facilitate this network access. And so it's critical that we don't leak information unnecessarily. Two things really became quickly apparent when we started thinking about the JRS. The first is, how should network access be provisioned? So what is the interface between the wireless user and the wireless network? And then, assuming that the user's been authenticated, what is the user then allowed to do? Is it just web-only access, or should IPv6 be mandatory? All sorts of things to think about. And as you can imagine, we had lots of very furious arguments about this. And the only way to really resolve it is to step out of the meeting room and actually do something. So UKERNA decides to proceed with a national trial called the Location Independent Networking National Trial to explore these issues. The first issue to resolve was the network access problem. What technology should we use to provision access to visitors? The two most popular technologies are called 802.1x, which we heard about in the first presentation, and, oops, this is an acronym that I haven't, okay, WRD, that is Web Redirect. Both use radius for authentication. I'll be talking a bit more about these two technologies shortly. However, although the two technologies are quite different, they do have one commonality, which is that they both use radius for the back-end authentication, which is convenient because it meant that all that we had to do for the LIN trial was implement a radius, effectively a radius trust fabric that connects up all of the institutions that were participating in the national trial. So we could have web redirects working alongside 802.1x. This is briefly how web redirect works. Web redirect is what is implemented actually at this conference. So those of you with laptops and have used the wireless network will be familiar with that. The roaming user issues a DHCP request to the network. The web redirect gateway sends back a response with an address and a DNS server of itself. So when the user opens a web browser and issues a request for any kind of host, the web redirect gateway just resolves whatever host it happens to be to itself. So whatever site the user tries to go to, it gets redirected to the web redirect gateway. That's why it's called web redirect. And this presents a login page to the user. The user plugs in their username and password. Assuming the credentials are correct, then the web redirect gateway opens up its firewall to permit traffic from the roaming user to the wider world, and then it also reconfigures its DNS so that it's no longer so broken, and the host can resolve things normally. So that's how Web Redirect works. Although this is IEEE 802.1x, although the diagram looks simpler, this is a bit of a fabrication. 802.1x is somewhat more complicated than Web Redirect. I've tried to keep the details to a minimum. Effectively, 802.1x uses a protocol called EAP, the Extensible Authentication Protocol. And this is between the roaming user and the access point. So this is difference number one, whereas with Web Redirect, that was between the user and the Web Redirect gateway, which is a host on the network, and the access point is just acting as sort of a transparent bridge, really. The access point here is actually involved in the negotiation. The access point doesn't do the actual authentication, it just passes the authentication request through to a back-end Radius server that performs the authentication. And then if the access point gets a, yes, this user is authenticated, then the access point forwards the user's traffic. So this is what our Radius fabric looks like, very roughly speaking. On the left, you've got an organization that has an 802.1x access point, and on the right, you've got an organization that's chosen to deploy Web Redirect. So say a user from the organization on the right-hand side of the diagram decides to go to the other organization and authenticates against the 802.1x access point. The authentication request gets forwarded up through the Radius hierarchy back to that user's home organization. The user is authenticated, hopefully, and gets access. And then likewise, with Web Redirect, we can go back the other way. So the Radius hierarchy is independent, really, of the authentication mechanism. These are the sorts of things that we discovered about Web Redirect in 802.1x. The benefits of Web Redirect. Obviously, excellent client support. Anything with a web browser will support this. This is basically the reason why Web Redirect is so popular. Unfortunately, 802.1x requires a special client on the wireless host that performs the authentication on behalf of the user. And the supplicant within Windows XP and Windows 2000 is particularly poor, is not very good. And many organizations have gone out and actually purchased third-party supplicants because the Windows implementation is so rubbish. This is a bit unfortunate because a lot of people's experience with 802.1x is through Windows, and they just automatically assume that, oh god, 802.1x is crap, but it's not. Windows is crap. If you use Macintosh, it's an excellent 802.1x implementation. Web Redirect is easy to use. It's a familiar interface to users. Users are just used to the concept of putting in a username and password. And perhaps most crucially, Web Redirect was already very widely deployed at the time we were thinking about this. The majority of institutions had already had some kind of Web Redirect system from vendors such as Vernier or BlueSocket. For that reason, obviously, these institutions were interested in maintaining their existing system. They didn't want to move to some new technology. What are the benefits of 802.1x? The main one is very strong end-to-end authentication. The user's credentials are protected using TLS, all the way from the user's supplicant back to the home organization. This provides very strong encryption of credentials. Unlike Web Redirect, where there's absolutely no link encryption, it's just a standard wireless connection. With 802.1x, you can use the WPA and WPA2 protocols that we heard about earlier, and these provide very strong protection of the link. And this is essential for accountability, because without that, with the Web Redirect system, for example, where there's no protection of the link integrity, someone can come along and easily spoof, as we'll see later. And finally, 802.1x does link-level isolation. This means that the wireless user is completely isolated from the rest of the network during authentication. And this contrasts with Web Redirect, where the roaming user is part of the entire wireless network during authentication, and this exposes a lot of problems. So, spoofing is a problem just by changing your IP or MAC address. This means that an attacker can spoof an authenticated user, pretend to be them, do naughty things. One of the big naughty things they can do is pretend to be the web redirect gateway, and they can collect users' credentials. And then, of course, they can also do man-in-the-middle attacks on any application data. Preventing and detecting this spoofing is extremely difficult. The only way it can really be prevented is through the use of HTTPS SSL certificates. But this is difficult because users have not been trained really to examine certificates. If a certificate problem pops up from the browser, they just click OK, 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 and they're in. They don't try and look at that. There's also no end-to-end protection of authentication. If you recall, going back to the radius hierarchy, we had a number of radius servers involved in that. With Web Redirect, the user's credentials are exposed at each radius server, which is a big problem. With 802.1x, the credentials are protected using TLS. And so they're not exposed. This becomes a particular problem in a roaming context because there are a lot of intermediate radius hosts. Within the context of a single institution, or so a conference like Terena, it's not a problem because the number of points of failure or points of compromise is relatively small. But in a very large radius hierarchy, you've got a lot of points of compromise or failure. So here's a summary. Mutual authentication. Web Redirect does, yes, but it requires users to be very diligent, and as we know, users aren't diligent. 802.1x does mutual authentication transparently to the user. 802.1x also provides accountability because you've got the link level isolation. And Web Redirect doesn't really observe the principle of minimal privilege because there's so much information leakage at each step in the radius proxy hierarchy. So for the JRS, we implemented 3 service tiers, and this really respected the fact that there was so much Web Redirect out there in the wild, we had to include it within the service. So JRS 1 is the lowest sort of security tier, and this permits the use of Web Redirect with security certificates from well-known certificate authorities. And then the other 2 tiers are sort of higher security, which require 802.1x with either WEP, WPA, or WPA2. The reason we permit WEP is not so much that we're interested in users' privacy. I'm not really particularly interested in users' privacy at all. What I'm interested in is accountability, which is I want to know that if someone's done something wrong, then I can get them for it. With WEP, yes, an attacker can read their traffic, but they can't masquerade as that user. They can't pretend to be that user. Accountability is crucial. Use of the network. This comes back to what should users be permitted to do. And this was, unlike the first problem, mainly a policy problem, not a technology problem. We went to institutions and asked them, how should we treat these users? We've got 4 basic answers. Treat them like local users. This is the easiest one. No configuration of firewalls. Second one, treat them like local users minus protocols X, Y, and Z. And this was generally because institutions thought that they should try and protect institutions thought they should try and protect visitors from themselves. So they shouldn't permit FTP because FTP is a weak protocol. My own opinion is that if a user wants to run the risk of using an insecure protocol, then they should be permitted to do so. They're adults. And the final 2 were very awkward. Some sites said that no protocol should be permitted except for virtual private networks. And then a completely opposite view, which is that everything should be permitted except for virtual private networks. Ask a simple question and you get a lot of very difficult responses. So what we did for the Janet roaming service, eventually we decided to mandate 21 protocols. I won't run through them here. And then institutions are encouraged to allow as many other protocols as local policy permits. Future work. We need to deprecate Web Redirect and preferably WEP as soon as possible. And this should be possible within 12 to 24 months. 802.1x is taking off very quickly now. The final problem really is binding, this is the way I like to phrase it, binding link and network identities. Within IP, there's no concept of binding an IP address to the the media address. So with the Ethernet, that's the MAC address. And this makes masquerading, spoofing very simple. There is, so for example, one problem is how do I know that the DHCP response I've got back from my DHCP server, how do I know that that really has come from the authorized DHCP server and not from another visitor who's trying to do a man-in-the-middle attack on me? Very difficult. There is a standard for DHCP version 4 authentication, but this requires shared keys, and besides, no one's implemented it, like a lot of these nice things. So there are some proprietary solutions, such as Cisco IP source card, but no standards. This is something that really needs to be looked at in a roaming context. And finally, one other possible solution, moving towards IPv6, is something called SEND, which is Secure Neighborhood Discovery. And this uses public key infrastructure X509 certificates to establish trust between visitors, roaming hosts, and the visited network and its routers, so that a visitor knows for certain that the router he's talking to is actually authorized to receive his traffic, and so the user is confident that there isn't a man-in-the-middle attack going on. So just the things I want to stress at the end. Focus on accountability and then privacy. With wireless, everyone's very focused on privacy, protecting just that very first hop from the laptop to the access point. Yes, that's kind of important, but in a roaming context, what's more important is establishing trust. And institutions need to be able to know that they can hold other people accountable if things go wrong. They don't want to carry the can themselves. Everyone has an opinion on security. Not saying who's right or wrong, but the important thing is to communicate and to listen to people. And when you've decided what you're going to do, explain why you're doing what you're doing. Otherwise, you'll just end up winding up a lot of people. One thing I've noticed is that managers are interested, understandably, very understandably, in providing a service. That's what they're there to do. That's how managers get, that's their metric, I guess, providing services. And security is, to some extent, a distraction from providing a service. So if you're if you're working in this kind of area, be prepared for a degree of resistance to implementing strong security. And finally, as I was saying earlier, strong link and authentication cryptography is a necessary condition, yes, but it's not sufficient for security in a large-scale roaming context. We need new protocols to establish trust between LAN nodes and to try and solve that binding problem. Okay. Thank you very much.
So, thank you, Josh, for this very interesting talk. Do we have questions? We have time for 1 or 2 questions. Oh, there's one.
Hi, Josh. Brian O'Hara from Trinity College in Dublin. I was just wondering, 2 questions. Do you get any problems in city centre universities with students of other universities using the service or misusing the service? And question number 2, it's somewhat related. You mentioned accountability, so I presume with 802.1x you have the authentication, evidence of authentication, but you actually log the traffic itself to see what people are doing.
Going to your first question about city centre universities, I'm not familiar with any problems that we've had to date. No. And then your second question was about logging of 802.1x. Logging the... Right. So was that logging of the authentication request itself or after authentication?
Yeah. Following authentication, you actually monitor this specific type of edge of roam traffic to ensure everybody is behaving themselves.
That's right. Yeah, sites are required to keep logs of connections.
Well, like you mentioned, for example, that proxies aren't encouraged.
Yes.
So what are you using to log the actual
well,
traffic?
we leave that up to institutions, just as long as institutions can assure us that they're doing the logging. So, for example, they might have a firewall that does the logging of connections, then we're happy. Proxies is one way of doing it. We didn't try to, wherever possible, we try not to mandate technologies. We just try and focus on aims and then leave it up to institutions to find technologies that they're happy with that meet those aims.
Okay, thanks. Let's thank the speaker again. Sorry, Klaas.
Sorry, I just wanted to quickly comment on this, on the first question of this gentleman. Eduroam was specifically designed to allow institutions to block other institutions if necessary, and that's because a lot of institutions were worried exactly about this problem. For instance, in Amsterdam you have 2 universities. One of them is spread out all through the city, and the other one is on sort of like a campus. The one spread out through the city was really worried. They said, yeah, we do all the access points through the city and they are going to use it. Well, it's a valid concern. So we designed the system that it is possible to block users. You are allowed to do that. You have to answer, of course, to questions why you are doing so. In reality, it has never happened, as far as I know, anywhere in Eduroam. So it seems that just having the ability to block it is enough for all institutions to happily work together in providing a great service also in the city centers.
Okay, so then let's move to the next topic, and it is about the surprise that it is not a need, not a must, that voice over IP is insecure, totally insecure, as I always experience it. And the presenter, we are very glad to have Eric Wenk.
Yeah.
Wenk here,
Yes.
very hard to pronounce for me. He is from one of the vendors selling wireless voice over IP phones from Cisco Systems, but here you are a distinguished engineer and you're specifically concerned with consultancy and advice in securing those systems. So, Eric, it's you.
Okay, and indeed, you're right. I selected the title to be provocative and to be a blunt statement, right? Is IP telephony become secure? I mean, we are mostly there. But all of us know that a secure system does not exist, or is basically powered off. And, of course, voice over IP phone, we want to get them usable. So it's not full security, that's just a blunt statement over there. But I've been really pissed off, if you allow me this wording, since years, by hearing presentation and over presentation, even a couple of months ago, that voice over IP is completely unsecure, and then using very old arguments that typically do not stand anymore. And this is basically why I put such a provocative statement there as a title. Also, it applies mainly for voice over IP within the enterprise, where all the traffic is within one organization, and where you can have controls on every pieces of devices. So, regarding security, voice over IP security has a slightly different strength than normal data security. A few things are identical. Reconnaissance, denial of services, and this kind of stuff, exploits. What we are doing in data, we do it in the voice as well, voice over IP as well. But there is a big difference. There's that voice over IP requires very good quality of service. So if there is, for instance, a denial of services in your network, or a worm ramping all over the place, degrading QoS, your voice over IP system will not get any attacks against integrity or confidentiality, but availability will be disrupted. So QoS is pretty important. The agenda for the session, basically, just a short introduction to voice over IP protocols, how do they work, to be followed by a risk analysis, which is typically what you are hearing everywhere. So I will go fast on this one. Then basically there are 2 ways to protect the voice over IP protocol. Because that's right, 5 years ago, they were pretty weak and vulnerable. You have two ways to secure, let's say, a soldier on a battlefield. Either the good old way, you provide him with a shield and a hammer. Basically, providing a shield outside of the soldier. This is the first point. Secure IP telephony through the infrastructure. The other way of securing voice over IP is to do some kind of magic and changing your soldier into a Superman, right? We need no shields or no hammer because it's secure per se. It's a Superman. That's basically how we can do it. So securing the voice over IP protocol itself. That's basically what IATF and other vendors has been done for years now. Okay. Just to be sure, because it's the wireless sections, how many of you would claim themselves knowledgeable or aware of voice over IP, SIP protocol, HTTP and so on? Can you raise the hand? Okay, that was what I was fearing, right? 5 out of the, I don't know, 100 in the room. So, oversimplifying, and due to time constraint, I put a lot of those slides as a reference at the end of my presentation. Yes, we can have a more deeper look there. So oversimplifying, you get two kinds of servers. On the left, this is the configuration server. And on the right, this is the SIP proxy or some kind of call center or call manager, as we call it internally. And on the bottom, you get real hardware phones, so real Ethernet phones. And how is it going? First, the phone boots, DHCP, ARP, blah, blah, TFTP maybe, or any kind of protocol to download configuration, check for new firmware upgrades, and so on. Then, it registers itself to the call controller, using SIP, for instance, or any kind of protocol, and starts some kind of signaling. At some point of time, it wants to reach another phone, right? I mean, the phones are there for using. So we start a media stream. And this is something a bit puzzling, because when you do HTTP, you get only one TCP connection. Okay? A lot of protocols, except FTP, have only one connection. Here, we've got two kinds of connections. The signaling between one phone and a call manager, okay, a call controller, and another streams of data, which actually typically used on UDP for quality of service, between two IP phones. And all those streams and all those connections don't follow the same path. And this will cause some challenge later. So again, the risk analysis, I refer you to about 8 slides at the end of this presentation. I oversimplify it here in 1 slide. First step, dynamic configuration. We are doing security. We know that dynamic configuration is a bad idea regarding security most of the time. You can spoof it. DHCP spoofing exists. Then you can run man-in-the-middle attack. Downloading firmware. That's an open door for Trojan. Right? I mean, nobody likes ActiveX, for instance. Why would you prefer to get TFTP or FTP, a firmware upgrade from a server? Right? Could be very dangerous. Signaling itself. Most of them. No authentication, no integrity, and so on. That's basically a normal server on the other side. Windows or Linux or whatever. Open to DOS. Or if you get a normal access, open to privilege escalations. So you can become root, for instance. The media stream, the UDP one. Again, no integrity, no confidentiality, and no authentication. The default one. And coming from Cisco, right? The middle bar in the middle, the network itself, basically it also can be unsecure. Okay? There are attacks, spoofing, for instance, or any kind of attacks against infrastructure. So the first step, the first way to secure voice over IP is to try to secure it by enforcing, providing shields and armor to an infrastructure, to the network itself. Basic stuff. I mean, hopefully you are already doing it in your network. Using SSH for configuration, using SNMP-v3 if you find a management system using it. Using role-based access control and some kind of reduced attack server as a backend. A lot of those papers published in 2000 and 2001 against voice over IP security and tools like Vomit or Kane and others are relying on layer 2 tricks, ARP spoofing, DHCP snooping, CAM overflows, and so on. There are now vendors able to cope with this.